Hello, Professor. In assignment 7.4.5, we are doing linear programming by using simplex method. The objective function is to minimize x equals y, x plus y, subject to x plus y greater than equal to 6, 3x minus y greater than equal to 9, x greater than equal to 0 and y greater than equal to 0. Now, converting the above inequality by subtracting the surplus value, since all the constraints are of greater than equal, we subtract the surplus value to each of the equation, namely y1, y2 respectively. Now, the problem is to x plus y minus y1 plus s1 equals to 6. 3x minus y minus y2 plus s2 equals 9. X greater than equal to 0, y greater than equal to 0, y1, y2, s1, s2, z greater than equal to 0. Artificial variables are added in order to make the equation balanced. Now, negative artificial variables add to t0 to constraints when they are of greater than equal to type. We are constructing the objective function to be better than its current value. First, we need to convert it to maximization. Minimize z equals minus maximization, and this is the formula, and so we require minus x minus y greater than equal to 0. So in order to make it less than equal to, we multiply it by minus 1 and add join to its original constraint set after adding the select variable z in order to avoid confusion with the other constraint. Now we have x plus y plus z plus s1 s2 equals to 0. The process giving us the constraint set like x plus y minus 1, s plus s1 equals to 6, 3x minus y minus y2 plus s2 equals 9. X plus y plus z plus s1 plus s2 equals 0 when x greater than equal to 0, y greater than equal to 0, y1, y2, s1, s2, z greater than equal to 0. Now form a table with the above constructs. We are using the construction and we create a table. So this table is created, and then there is some y8 representing the basic variable. Dependent variable is s1, s2 and z. Independent variable are x equals y equals 0. Extreme point is xy equals 0, 0. Value of objective function is z equals 0. Optimal testing, the entering variable is x corresponding to the least variable 1. In the last row, since there is more than one value, we choose to corresponding to x. And feasible testing, compute to the ratio for the RHS divided by the coefficient in the column labeled x to determine the minimum positive ratio. Choosing x2 corresponding to the minimum positive ratio 3 as an existing variable, since we always aim to write off the artificial variable from the basis. Divided the row constraint, the existing variable, by the coefficient of 1 for the entering variable in the row. Then eliminate the entering variable x for the remaining rows, which do not constrain the existing variable as 2 and have a 0 coefficient for it. And we can as a result we summarize the below table. This is the table we are getting, and y8 represent the basic variable. Depending variable is as usual s2, y1 and z. Independent variable s1 equals 0, y equals 3, and extreme point is xy equals 0, 3, and value for the objective functions z equals 3. Optimally tested, the entering variable is y, corresponding to the least variable 1.3333 in the last row. And the feasible test compute to ratio of RS divided by the coefficient in the column labeled y to determine the minimum positive ratio. Choose S1 corresponding to the minimum positive ratio 2.25 as the extreme variable, since we always aim to write off the artificial variable from the basis. Divide the row constraint the existing variable, the first row in the case, by the coefficient of the entering variable in the row, the coefficient of y in this case, giving a coefficient of 1 for entering variable in this row. Then eliminate the entering variable y from the remaining rows which do not contain the existing variable s1 and have a 0 coefficient for it. And we can see that minimum value z equals -6 of the objective function, xy equals 3.75 and 2.25. This maximum value is objective is the 2.25. And now Professor, I'm working on code, and as soon as the code is ready I will submit. Thank you.